All right, so we have some very exciting stuff to cover in this video, which is the culmination of everything that we've pretty much worked on in this entire class. And, obviously more recently working with limits, which is at the beginning of class, I introduced this idea of the derivative. I said it gives us the slope of a function. It represents a rate of change. It's a comparison of two tiny things. And I just said, look, here's the tool, here's the hammer, use it, go build some stuff. I'm going to tell you how this tool came to be in the future. And we have finally arrived at that day. And so this video is going to require, if you've ever been interested in pure mathematics or what it's like to really think about math, kind of on this big brain sort of level and how this sort of math, comes into being, this video is for you. And if not, well, I don't know, maybe if you stick around, you'll like it. But anywho, so the limit definition of the derivative, aka where does the derivative come from? So the idea that we're going to try and tackle, or the idea that mathematicians had, or rather the question is, how do we find slope? Okay, how do we find slope of something curved? Right? Because, this curved graph is always changing. How do we find the slope of something that's curved? And a first idea might be to use our algebra 1 skills and, to pick a second point over here. And maybe I'll call it, let's say that if this first point here is at some point x, it may be okay to say, okay, let's go some distance over, and this part might seem a little weird, but let's go some distance over. We're going to call this h. So this next value here, I know normally we would call this like x2 or something, but we're going to call this point, this particular x value, just x plus h, which makes this point, x plus h, comma, and then the y value, which would just be f of x plus h. And I know this notation seems a little weird, like, why are we calling it h? Why are we putting it? Why don't we just call them x1, y1, x2, y2? It's more just to match the, how it's written down in the textbook, but you could use x1, y1, x2, y2, all the same. But the point is that if I wanted to try and calculate the slope at, say, this particular point, a good first try would be to do exactly what we've done here, is to grab a second point and draw a straight line between them and calculate the slope. And we would say, okay, well, slope, let's see, slope, that's going to equal, it's going to be my y2, my second y value, minus my first y value, and then all over, it goes y2 minus y1 over x2 minus x1, right? This is how we calculate the slope, all right? And if we want to tie these things up, if this looks super foreign to you, again, just you can think about it as this is the same thing as if I had y2 minus y1 over x2 minus x1. This right here is my rise overrun from algebra class. Okay, we're just using a slightly different notation, but it's the exact same thing. Just when we talk about slope, this is how we calculate it. And we might notice a couple things. First and foremost, right, in our little slope formula that we've come up with, you may notice that in how I've chosen to pick my x's, that, I'm going to have x plus h minus x, which, is going to kind of simplify down to f of x plus h minus f of x all over just h. Okay. Now over here, if you like to think about this as rise and run, you can think about this is delta y, and this right here is delta x. And I'm putting these triangles because technically speaking, right, this is not the infinitely small change in x and y that you and I know and love. This is like a measurable, this is what we call a measurable change in x and y. And what I mean by that is if I go here, right, you can kind of see that this is a huge chunk, right? There's a huge change going on. So this h right here is my delta x, if you will. It's my gap between those two particular x values. But the point of this is not to confuse you with the notation. The point is simply, look, I would grab a second point here, right, and I would just calculate the slope. Just using, that's the only tool I have. I don't know what a derivative is. This is all I've got. And clearly this is not like a good estimate, right? Because the slope of this line is kind of like that, and the slope of where we actually are is kind of like this. They're not exactly super close. But now that we have a new tool, which we call a limit, we can do cool things. And one of those cool things that we can do is we can say, oh, well, what happens if I take this particular point, this x value here? If I take this point and I slide it closer to x, right? Basically, this yellow point, is going to slide down, and it's going to make its way closer. And the idea is that if we were to get those points infinitely close to each other, right, as close as possible before they touch, then in theory, my estimate, right, this line that I'm going to have is going to get better and better and better, and the slope of it is going to eventually start to match the line very, very well. And so the big idea here is that, on a microscopic level, you can remember from the first day of classes, I took this thing and I said on a microscopic level, what's going on here is that if we're zoomed in close enough, this pink graph no longer appears, curved anymore. It's going to look like a straight line, and maybe I'll try and get it to match the current drawing, right? It's going to look like a straight line. And this yellow point is going to be, in theory, we're gonna call this distance here like infinitely close. Okay, we're now infinitely close. And now we're talking about being on this kind of microscopic level where now the delta y, or change in y, is infinitely small, and we're going to call it dy. And this delta x is going to be some infinitely small dx. Okay, so this, our delta, our change in our x values, is now just infinitely small. All right, so this was the idea from the very first day of class that we had, but now we're going to try and represent this using limits. And we're going to say, okay, so in English, what's going on? Right, in English, what we're going to do is we're going to, ask ourselves, what is the slope of f of x between, I guess, I won't even say f of x. We'll just say, what is the slope between those 2 points, right? Between the 2 points, right? So we have x plus h, comma, f of x plus h, and the points in question, x, comma, f of x, right? What is the slope between those 2 points as we slide the points infinitely close together, right? As we slide the points infinitely close together. Okay, what is the slope, right? AKA, as our gap between the points gets smaller, as this gap starts to decrease, you could say AKA, as you could say as x plus h, as that particular x value approaches our x, or if you prefer to think about it, as basically h approaches 0, which you can kind of see. We can do a little algebra here. If I subtract x from both sides, I get h approaches 0. Basically just saying, as this gap gets really, really small, right, what's the slope? Right? What is the slope? Right? And so this manifests itself in the following way. This basically looks, we're going to say that our answer for slope is going to equal the limit as h approaches 0 of f of x plus h minus f of x over h. Okay? And this thing, this formula right here, this mathematical idea is the limit definition. It is the limit definition of the derivative of f of x. Okay? This is it. This thing, it may not seem like it, But if you understand what a limit is, and you understand what this thing says, right? Remember that this thing right here is just slope. It is the slope between 2 points on a function, and all we're doing is we're saying, all right, we're going to sit those points really, really close together. What is the slope? And if you can understand that, then you understand the idea of, oh, so the notion of a derivative, the notion of finding slope, came from the idea of sliding these 2 points together and calculating the slope using just y2 minus y1 over x2 minus x1. That's where this little formula comes from. Now, granted, it looks very weird, and I will grant you that, advanced mathematics tends to look a little bit strange when you're not super well versed in it. So I think I'll just show you an example of how, mathematicians tried to use this. So once someone came up with this, they said, so for instance, can I find the derivative of y is equal to x squared. Okay, find the derivative of y is equal to x squared, and I'm going to specify using the limit definition of the derivative. I understand that the derivative is y equals 2x because I gave you the tool, but for now we're going to pretend that we don't just have the ability to take the derivative, and that we haven't proven how the derivative works and all that stuff, and we're going to use this very rudimentary and crude method of calculating the derivative. And what do I mean? Well, all we need to do this thing is we're going to be doing a limit, but we need to know first and foremost what f of x is, and f of x is given to us, that's just x squared. And the only other thing I really need is what is f of x plus h? Well, f of x plus h, that's just going to be x plus h squared, and even that in and of itself is x squared plus 2xh plus h squared, right? And so now all I'm going to do is I'm going to plug that into my little slope formula, right? We're just going to use the limit definition as it stands. And so we're going to get that we have the limit, right? So this means that we have the limit as h approaches 0, right? As the gap gets really small, right? We're going to have x squared plus 2xh plus h squared minus x squared all over h. And you may notice, right, that in the last video I talked about, that one of our tricks is to take things like this and to expand them out. And so maybe I shouldn't have done that before I, filled everything in, but the reason is you'll notice that if I just, was just looking at this, you might be like, well, I have an h equals 0 in the bottom, I'm dividing by 0, can't do that. I need to be able to evaluate this limit, so we got to try something. And so one of the ideas is that instead of leaving this term as x plus h squared, if we multiply it out, if we FOIL it out, you're going to notice that first x squared and the second x squared cancel out. And when they cancel out, they're going to let us be able to evaluate this derivative, or rather this limit, I guess. Because we're going to get 2xh plus h squared over h, and now we can cancel out the h's, or at least some of them, and we're going to get the limit as h approaches 0 of 2x plus h, because the one that's in the denominator will cancel out with one of each of those, and now we can take the limit, and lo and behold, we get 2x. And so that means that the slope of our function, y equals x squared, is going to be 2x. That is the derivative of x squared. That is the derivative that you and I both know and love and what we expected to get. I think maybe I'll do one more example, which is, we could do a case-by-case basis for a lot of these, but maybe I'll do one that's kind of fun, or at least I'll set it up and maybe I'll put it on the homework. But I'm going to say, let's prove the power rule. Okay, let's prove the power rule for derivatives. Prove the power rule for derivatives, right? Because, mathematicians had to first come up with this idea of like, okay, well, how do we talk about the slope of something curved? Then they said, okay, well, we have this tool, which is, this limit tool, which is a very rudimentary, crude tool, and we're going to take the limit of all these slopes. All right, cool, no problem. But they didn't want to do it over and over again, right? And so far, we have a whole bunch of rules. We have the power rule, right? We have the product rule. We have the quotient rule. We have the chain rule, right? We have so many derivative rules that someone had to go and prove and do the math for and be like, this is why it is the way it is. We are going to try and take a crack at doing just one of them, which is the power rule. And so in order to show this, we would have to show, we basically want to show that if we're given y is equal to x to the n, where n is some real number, right, then the derivative y prime should equal n times x to the n minus 1. That's what we get. That's what we want to show. And so we're going to use the limit definition that we came up with, this rudimentary but very, very fundamental thing that's going to help us prove the power rule. And so we're going to need to know what f of x is. F of x is x to the n. And f of x plus h is going to equal x plus h raised to the n power. And so when we plug this stuff into our limit, we're going to have the limit as h approaches 0 of x plus h raised to the n minus x to the n all over h. Now at this point, you may notice a theme. I have an h here. Can't evaluate. I got h approaches 0. Can't evaluate. I get 0 in the denominator. Makes me very sad, right? And one of the tools, one of the tricks that we have for dealing with limits like this is to expand things out. Now, granted, none of us probably at this level have taken a class in combinatorics. And so, we may not be familiar with how the binomial expansion theorem works, which is fine. The idea is I'm going to have you're going to need to put some faith in me. And I claim that this thing, if I were to take, x plus h, and I were to multiply it out, right? If I were to do two of them, I'm going to get x squared plus 2xh plus h squared, right? And then if I take that and I multiply it by a third x plus h, right? What would we get? Well, I'm definitely going to be guaranteed an x cubed. Now I've got a 2x squared h. I've got an xh squared. And then I'm going to get an hx squared. I'm going to get a 3xh squared. And then I'm going to plus h cubed. And so I'll just do this set really quick. So I have x cubed plus 2x squared h plus... let's see, x squared h, I got x squared h, I guess I have 3x squared h now. So I have 3x squared h, courtesy of those. Then I'm going to have 3xh squared. Oh no, this is supposed to be a xh squared. Yeah, this should be a 2, so this is going to give me 3xh squared and plus h cubed. And the point is, right, the point of me doing this is what I'm trying to say is that this thing here is going to give us the limit as h approaches 0, that if I do this n times, I'm for sure going to have an x to the n term in the front, and then plus a whole bunch of stuff that has h's. And I claim that, we can try and use this one as an example, but in this particular case here, when n is equal to 3, aka I've done x plus h times x plus h times x plus h, you're going to notice that this number in front is n, and the exponent on this is n minus 1. Okay? One more thing you're going to have to notice is that there's only one h attached to this first term. There's two h's here, and there's three h's here. And I claim, basically, the point of me doing this is that in the long run, that I'm going to have an x to the n, and then I'm going to have n, x to the n minus 1 h, and then I'm going to get n minus 1, x to the n minus 2, h squared plus ... And this pattern will continue until basically I hit plus h to the n. All right? And so I'm just going to kind of write that down. I'm going to say, okay, I claim that I get n times x to the n minus 1h, and then I get plus, n minus 1, x to the n minus 2, h squared, plus dot, 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 plus h to the n. And then, oops, I'm kind of getting tight here on space, very sorry, I have minus x to the n, and then all over h again. And the point of doing this, the point of me going through this long process is that, look, this x to the n here is going to cancel with this x to the n here, and then all of the resulting terms are all going to have at least one h in them, which means I can cancel some stuff out. I can say, oh, okay, so this is going to give me the limit as h approaches 0 of n x to the n minus 1 plus n minus 1 x to the n minus 2 h plus dot, 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 plus h to the n minus 1. And now, because there's no more h in the denominator, and notice the only ones that have h attached to it are all of these remaining terms. Every single one of these remaining terms has an h attached to it. And so when I evaluate the limit as h approaches 0, the only thing that's going to be left standing is n times x to the n minus 1. Whew, that was crazy. The whole point is that I'm not here. I'm not going to sit here and make you prove this, or at least I don't plan on making you prove this. But the point is that, in math, in calculus, right, you were supposed to start this class with all of this material. And hopefully you are thankful that we didn't start all of this class with all of this material. Because I know when I was a student, my mind would have just been melting out my ear holes. But the point is that there is pure math that exists. And there's ideas that it comes from very, very simple ideas. The idea of taking slope and just applying a limit to it and saying, oh, that should, in theory, give us the answer. And once we have that, then we can use it and we can do some quite interesting and more difficult math. We can find the derivative of x squared. We can take it and generalize it to finding the derivative of x to the n, and so on and so forth. And thankfully for us, other people who are much smarter than all of us have taken the time to prove that the product rule works, that the quotient rule works, that the chain rule works, all of those things for us. And I just wanted to show you the power rule is kind of like, hey, this is how you can do some pure mathematics. This is how you can do some advanced mathematics. But yeah, I think for the intent of homework and things you might see, solving problems like this where it's use the limit definition to prove the first derivative of x squared is 2x, it's going to look something of this nature. So again, hopefully that was interesting. We've done it. We finally uncovered where the heck the derivative came from, where it came from as an idea, and how we use it, how we use the limit to actually calculate derivatives the long way. Unless it says it on the homework, I'm not going to make you use the limit definition, to calculate derivatives or stuff. It could show up on the quiz, it could show up on the final, it could show up on the homework, but I'm basically saying that, going forward, you probably won't ever have to use this again unless you end up pursuing pure mathematics. But the point is it's just supposed to be an introduction to kind of this higher level thinking of math. So hopefully that was interesting. And if you made it to this point, we are done with derivatives. And the last thing that we're going to cover this next week is basically, how to go backwards from a derivative. But you don't have to worry about that until you are ready. So hopefully this is interesting as always. And then when you're ready, head on over to the next one.